Okay, so should I wait until the ball comes? She's talking. Yeah, I need to. See the coffee mark, tea mark from there? Not supposed to see it. Anyway, so a student of mine who finished PhD, Nathan Moshman, a year ago in Naval Postgraduate School, his thesis is maybe is worthwhile mentioning here, and then of course I'm not going to talk about his multi-phase flow and so forth. But the problem is the following. You know, when the rocket launching station, we have NASA scientists also in our university, including astronauts and people like that. So when the rocket takes off from the launching pad, right, it takes off, you know, you see that this big flame going downwards. So when the flame impinges on the launch platform, a shock wave comes and damages the fuselage of the body, you know, frame of the rocket. So they have a problem. So the way NASA has been dealing with that is as the rocket takes off, they have big pipe spray water. Big, very big pipe, you know, my height, diameter. You can actually see by water injection. And so the water injection apparently because they evaporate, takes the energy away from the fluid, and also when the shock wave passes through a liquid drop, it essentially pulverizes the liquid drop, make it breaks up. In doing that, shock wave loses strength, and so these are the mechanisms they were interested in. And he was so Nathan Moshman. So this problem was posed to us, and of course, you know, I've been thinking about flow control for many years. So it's natural for us to think about the control problem. So Nathan Moshman's thesis was computational simulation of one-dimensional system, because it's you wanted to compute. Or if you want to prove it's even harder, hyperbolic conservation laws of fluid dynamics, 1D. Governing multi-phase fluid flow. So multi-phase means there's gases and there's liquid also inside. Here we talk about much simpler situation. And what is the control? What's the control in there? Can you tell? What is the control? I told you it's like telling a riddle, noddy, right? I just told you a story, and I'm asking what is the control in this PDE? We are controlling, right? That's these liquid drops. So most easiest way to think about is you can think of it as mass injection in the field, right? So in the system of equations we had, it's a hyperbolic system. The control is applied in the first equation, the equation of continuity, mass, because as injection, and he developed the control theory and even calculated and shows that he can, you know, prevent the shock wave or delay the shock wave and things like that. Theoretically and computationally, that's a very cutting edge type of problem, is very cutting edge. So the reason I raised is that so when we say I take a volume of region and then I'm focusing my interest on how that region evolves in time. And so nothing prevents you to actually, it's very likely that you will run into situations where some engineer or one of your colleague, or maybe your own, you choose to work on some research labs or companies or want to have some research projects, and they pose problems where a certain mass injection is created in the. So that can come on the right hand side, right? it can come as in the problem I was talking about is actually very difficult because you inject the water and the droplets move in space. So even if they say they are fixed in space, or maybe a continuous distribution of, so that can be maybe modeled this way. You can say the rate of change of mass in the volume, right, is equal to maybe in that volume omega t some source which is a function of y and t and dy, right? Does it? So this is like the source. Because this is the rate of increase, and that's equal to the amount of. So if there is no source or sink in the domain, then you set this to 0, right? Anyway, so let's say this is that's one remark. Okay, so this is a remark, and 0 if no source or sink. Sink is when they are in spaces where some mechanism by which the fluid is disappearing. Fluid or whatever the quantity you are, right? So this part is separate. This is not always 0, but it is 0 if you put this condition. That is, yeah.
Suppose it is a closed domain, it will be 0. So
say it again.
the domain is closed.
It is closed.
Then there is no source come to.
No, it's everywhere inside. You know, there are the fluid is moving, let's say, and then maybe there is some pipes which 0 diameter injecting, spraying water. If you actually, another story. Arizona in the US is well known for very warm temperature. In the summer, in particular, it can go to 110, 120, 115 Fahrenheit. I know Madras will that's nothing by, but this is very dry, and also humidity is very low. So when I was a student in Tucson, Arizona, my PhD, and you know, summer you don't get out because it's. But then maybe about 5-6 years ago, I went to Arizona State University, which is in Phoenix, Arizona. And I noticed that in the downtown, there are you know, this spraying. They are spraying in the right. They are the injection. So of course it's done in localized, but it's like creating this evaporation. So that that's more complex physics than this one. But you cannot say that well this d omega is close. I am not leaving any piece open. That's nothing to do with this. It is, think of this as you are spraying or introducing mass, right, in sink, right? I am telling you stories because these are real. Somebody asks you to estimate how much you need to inject. So anyway, that is one remark. We will come back to this. Here, if I want, I can actually, this was a scalar. Remember in our calculation, f was a scalar function. In my Coimbatore lecture, we went, you know, extensively to look at arbitrary coordinate system, divergence in contravariant, covariant derivatives. But if we simply say Cartesian, we don't worry much about it. Notice that I can actually make it some index k, and that k is carried, and then this is true for k is equal to 1 to some m, right? Agree? Right, so that I parameterize, so that this whole equation is can be, you can introduce an index here. U is already a vector. Yeah, k is some index, right? So if right, okay, it makes it a system, right? So now it is a system of equations, k running from 1 to n. Agreed? Agreed. So all this calculation I did this morning is valid still if this is a system, right? The k can run from exactly 1 to m. You know, remember this is a summation. So this k can this is already for any k. This is already a summation between in I is equal to 1 to m. But I can introduce another parameter. So that's an important thing to say. Okay, now let's go back and finish this this calculation. I erased this one. I made a remark, and we'll come back to this remark. Without doing any extra calculation, you just this is true. I also want to get rid of the source, so that we finish this calculation, and then we'll worry about. Okay, after all this, now what is this equal to? I want to take this d by dt inside. So what will it become? Omega t? Yeah. Partial rho by t plus div of the y coordinate of rho u dy. So far it is not, there is no fluid mechanics or anything applied. I just, instead of F, I call it rho, right? Now, if no so sink, so then d by dt of omega t rho yt dy has to be 0, right? Rate of change of mass in a volume is 0 because you are not injecting any mass, you are not taking out. It is 0 it's a reasonably mathematical argument. You can go in and bring a fundamental theorem of calculus to finish this story, but it's a reasonably mathematical argument saying that if there is no source or sink anywhere in the flow domain, then this should hold for any omega, right? It should hold for any omega, no matter how small you take, and therefore this should be 0 for any omega. And if the integrand is continuous, then you should have pointwise statement that this implies. This is where you immediately use a sort of like a heuristic, but there is if the functions are continuous, then you can complete it rigorously. You end up with this equation, right? Omega t can be chosen arbitrarily small. So you can argue that in order to do that, you have this phi should be invertible, then you should be able to take any little omega and the whole calculation would go through. But suppose all that is true, then this is true, right? Everybody agree with this step? So there is no, there's another derivation in fluid mechanics where they take a box and then fluid comes here, fluid goes out and so forth. That is a little bit more, initially maybe it's easy to understand, but this is a much better equation. So this is the equation of continuity. Before going to run to incompressible constant density flow, ocean. So I'm a Navy person, so I didn't intend to be a Navy scholar, but I ended up somehow being. Navy is very interested in vehicles on the surface. So is Indian Navy, by the way, or vehicles beneath the surface, right? Submarines, torpedoes, and various sensors. And as you go to different depths, what is the most obvious change you probably heard of? The pressure is, yeah, but that's we haven't spoken pressure yet. So the density changes, right? The density changes and it creates very interesting dynamics. Density changes and it even changes abruptly in places. Those are called thermoclines, and those they create gravity waves, and so those are very interesting for Navy because you can see them from various detection. Anyway, so the rho changes, density changes. So the most interesting problem on the planet dynamics of ocean, where all the mathematics and poems and everything being written about, the good model is actually incompressible hydrodynamics, but density varies, right? So we should not rush to go and say that okay, density is constant and now we run to the Navier-Stokes. Navier-Stokes, for some recent historic purpose, became sort of in the front of our attention, but so the density change is very significant in problems. So we keep that variation, density variation. But so in situations where the density variation is not significant, notice that so if rho xt is a constant, let's put it rho yt because I'm not using x axis for the original position. What happens to this equation?
That's 0.
This is 0.
As rho is constant to 0.
So that becomes div of u, because c is comes out and we throw it away. Div of y of u is equal to 0, right? Let's write it out. It is du1 by dy1.
dun by dy is equal to 0.
This is called the divergence free condition sometimes. It's also called the incompressibility condition. The divergence free fields are special because they also share this kind of properties from magnetic fields and electric fields and so forth. So anyway, so that gives you the first equation. We have derived it without any just by starting. It looks almost like a part of calculus, right? So far it is, you can see it's a part of differential calculus. Do you agree or do you disagree? So far I haven't used anything about the notion of physics yet, right? That comes in the next step when we go to the momentum equation. Until then, this one is just the transport equation rewritten in another way. Can I erase this part? Okay, so let me rewrite this. So this term, remember it is written as d of f of u1 by dy1 dot d of f un d by n. And if f is again further parameterized by k, then that's a free variable. You need to remember that because if we are about to run into that situation. So far we haven't spoken about what's called equation of motion. That comes in this next step. So that is called the momentum equation, and or you could say momentum conservation if there is no force involved, but we are going to involve some force. So we spoke about the mass of this this blob we looked at. How do you get the momentum? What's the momentum? Mass times velocity for particle which. So this is so the following expression has the meaning of momentum, and you would agree. So you have rho of u of y of t, rho of y of t. dy. So this is the Lebesgue measure. So that much is the mass, and u is the velocity. Notice that u is a vector, so now maybe I should note that this is a scalar, this is a vector, so this is n quantities, right? Agree? So, so we are interested in the rate of change of this quantity. What is it equal to? Say it again. Yeah, yeah, that's the physics of it. Let's not go there. I want to rewrite. Remember, I have a d by dt, I want to take it inside. That's what this morning is about. How to take the d by dt inside. How do you take it inside? Do we have to do all that, or maybe you'll just use this one? Yeah, but there's a problem. In the morning we had a scalar here, and now I have a vector here, right? u1 to un. But then I made a remark that I can parameterize this by k, still the whole calculations go through, right? So let's see with how many of you like tensors? Those students with, I spent them 20 lectures last time in my July lecture, so now they like tensors, not just in Cartesian, but I hope you like Christoffel symbols and so forth. We are going to see a little bit of that. So we want to take it inside. The idea is same. Essentially go and write the same thing here. So I'm going to regard this as my rho of u, but with a parameter here, right? So what I would do is, remember I worked with the k, so I will write this k, right? Because I said I can use a k here. The whole thing goes through if I have a k here. Yeah. Agreed? The k can be from 1 to, let's say, n, right? The same dimension as. So help me write this on the right hand side. This is equal to omega 2. This is where you are about to go back to the original domain and so forth. So this is equal to. Okay, so the first term is same, right? So it is d of rho u k by dt, correct? And the divergence, you need to write the divergence. So you can write the divergence, this term with another parameter if you like. If you want, you can write that one as d of fk ui over d yi. When I repeat the index, I am summing, correct? That's equal to this quantity. You know, this, in effect, you have this one here, but I never write it. This is everybody is comfortable with that, right? Okay, so this term, if you help me with this one, then we are in very good shape. So, what is this term is going to look like? First tensorially, d by d y k o I. How many for I? You have 1 more hour. Okay, so let's go back. Yeah. Okay, so notice that the k is free. I want to keep it. I'm not going to make you k. I keep it. So don't touch the k, right? K I keep it. So in this equation, if you look at it, I don't by fiscal law I fix k. You can't change k, but there's a summation here. That is in I, right? Now if you come back and look at this equation, there is actually that k. I picked by picking this one, parameterizing this vector by a k. Now I have a vector, but I just say index. So this one is I of rho ui uk. Very good. Right? dy. So notice that the k is a free variable here, and here after the summation k is still a free variable here, right? So we are in the correct path. So that's people also write this one in vector notation. In the vector notation, this equation is stated this way. Sometimes they put an arrow there. Dy is equal to omega t, and you write this as d of rho u by dt plus div of y dot, and then you write u and dy. Now you want to help me, how do I write this one? There are two u's there, right? Is that a dot product? There is some noise in the front saying that is a tensor product. Is it a dot product? Is it u dot u?
No.
It's not, right? Because notice that I have ui and uj, I can forget the summation. I can vary freely. So that's what's called the tensor product, right? So this should be u. I'm also in this way demonstrating the difficulty in vector notations, because you don't know which one you are summing against when you write in vector notation. So usually you're the first guy, but in the tensor notation is obvious, it's override. Anyway, so this is called the tensor product, and it has to be a tensor product because I just multiply this and I had to take all possibilities of I and k going from 1 to n. Okay, so that all we have managed to do is to apply the transport theorem correctly to what as an integral we call the momentum, right? We said the mass times u expressed as this integral. The rate of change is actually can be expressed, this d by dt can be brought inside, and we write it this way. So now we can speak about some law of fluid mechanics, right? And that's where all the, so until now there is no fluid mechanics here, it's just calculus, right? Honest calculus, right? No, I didn't say anything about I didn't demand any physical, maybe in setting that omega arbitrarily small, but that is just fudging your way through fundamental theorem of calculus or something like that. But here now we have to say something about the force. It also, just like we spoke about control introducing in the mass equation, there is also is possible to talk about control in the momentum. Usually people associate applying control to applying a force, right? And therefore now you can say where the control should appear. If there's so maybe that should appear as a force. But what do you mean by force in a distributed way? There should be some other mechanism should come in, just like the injecting the mass. There should be some other mechanism to bring force in a distributed way in any arbitrary volume, right? In fact, in magnetic flows, you do have the magnetic fields. If you have a flow which is conducting, they do turn the fluid. In fact, the solar flares, which is called whenever you have a coronal mass injection from the sun, so much of ionized gases rush toward the earth, and they flow around the earth rather than coming and hitting us, so damaging the electronic equipments. It's because of the magnetic fields of the earth, they deflect. So it is known that there are body forces, what's called body forces, forces that appear as right hand side to the momentum equation. But right now, okay, those are not there, right? I'm not applying any magnetic fields. There is no gravity, the notion of gravity we don't need. So there should be some other force. That is the most puzzling and difficult concept in fluid mechanics. This is the stress, concept of stress. I think maybe also in statistical mechanics derivation, which we will see maybe that may make more sense to you, because that you have an average velocity, a collective behavior. It's like, okay, I spoke about, a group of people moving like a fluid, and one or two don't want to do that, and then that creates a stress, right? So that's it's more connected to that kind of philosophical ideas when you start in the statistical mechanics. In the continuum mechanics characterization here, the stress comes not that convincingly, I think. But so the argument is something like, when you cut out any domain, you are not actually leaving a void here. So there should be some force that is in balance between the domain you leave out. This arbitrarily, you think of, you're not actually cutting out, but suppose you remove this part, so there should be a force appearing on this surface, and so that force is essentially the material force inserted from here to here, and so that has to be, that is the what's called the stress force, and you can study more of how this is derived in fluid mechanics classes, but so I want to leave these two sides. Now you understood the transport theorem, so we get rid of that. And so that force, so let's take a piece of the domain d omega, and let's say this is the normal n. So if you take a piece of the small piece here and compute, so this is the stress force. At this point, I actually will write down what you should get, and I'll request you to go and read. So you write it sigma, you write it maybe first tensorially, njds. That's not the notation I want to have. I wanted to have the k as the free index, and I sum over I. The stress is actually defined, the first k actually signifies in the direction. The second index actually defines on which plane is acting. Plane is characterized by its normal. So, I let you go and read, because it is sort of a math lecture. So, or you can write it as d omega sigma dot n ds, but it's a bad notation. Notice that this is a tensor, this is a vector. So sometimes people write two lines and two line, for the tensor, and one line for the vector. Okay, so the argument is that the integral of this one essentially gives you the force exerted by the surrounding fluid on this volume, and in the direction of k. Agreed? K is the free index, is the direction, and therefore you equate that. This integral should be equated to this integral. This is the okay. So if you do that, I'm looking for a place to write. Which one you want me to keep? This side or that side you like? How many for tensor, how many for vector? I'm sure this is more transparent. Yes, the left, because it's more transparent. That side is, you don't know which side you are taking dot, right? So may I keep that side? Okay. So, dy. So this is equal to so the left side is equal to omega t, the rate of change of momentum, right? The left side is rate of change of momentum. So in essence, we are applying Newton's law, and it's not that particularly convincing application of the Newton's law. You know, so this is equal to. So I write it here. It is d rho uk by dt plus this part is d by dyi rho ui uk dy. It doesn't matter with this order, right? So this is equal to a surface integral sigma ki ni ds. Right? We want to close the story and we want to get a differential equation. But let me slow down and see. This much you are with me? Right? Maybe you didn't like this argument. If you like it, then maybe you didn't see. There is, if you go and look at Hermann Schlichting's book, maybe because the book I studied by there's no Germans here, so then I can misspell. Is not correct. Huh? Is it correct? Schlichting? Yes. Schlichting. We used to call it Schichling. So Hermann Schlichting book is the classic because they do this one in several chapters, which I do in one line, taking these prisms and looking at various planes and how the stress is how this is arrived. If you don't feel comfortable the way this speaker wrote it, so this is called the boundary layer theory.
Available in Indian edition.
We'll talk about what's the boundary layer maybe. Okay, so so essentially this is the first time we applied some physics, Newton's law, but we ended up with a volume integral and a surface integral, right? So we want to maybe either take this guy to the boundary or maybe this one inside. This one inside, so that maybe you can derive a differential equation. That was they were looking into a differential equalization characterization. Why? Why? Because it's you are interested in differential equation. It's a combination of derivatives. It's a point-wise characterization of the fluid, right? What's happening at a point? So you want to get a partial differential equation at a point in the flow field, and you are trying to get to that. What does it mean? So that's why you start with the conservation law. Sometimes if you in numerical calculation, you go back to the conservation law. Okay, now so the reason why I'm slow down here is I'm going to give instantaneous assignment. Now how do you go back to a volume integral? Let's get it on that page because that's probably the most sophisticated one and you can go back and read about it. Schlichting is one of the best places to look at it. The notation is not redundant, it's done in every component. This is why the book is a classic. Every engineer who studied fluid mechanics has read that book. So help me to take it. What am I doing here with this II? You are summing it, right? So that is being summed out. It's not a free index anymore. So the whole thing, is it a tensor or a vector? How many for tensor? How many for vector? How many is scared of these things? You summed over I, and therefore it's a free index is k. So the free index is k of that entity, so you are taking from 1 to n, right? So this behaves like a vector, right? Let's take a minute so that we do this one carefully. I have already used f, so let's use some kind of g of k, g of I, sorry. Yeah, g of k is okay, g of k, that's okay. So I want you to do a magic for a moment. I want you to help me to recall a theorem we need. It's called the divergence theorem, Green's theorem. So how does it look like? Omega divergence theorem. Div of a vector is transformed to surface. So it is div of, let's say, G dy is equal to d omega G dot n ds. Okay, so let's now go back and so this is a vector here. So let's write it in tensor so that we can go to this guy. So now you write it, I don't care it's a function of time or not. By the way, this is a d omega t in case is the boundary of that. Let's write it in tensor so that you see it better. So this is d gi by dy, dy means d by 1 to dn is equal to d omega. What is this?
0 time.
Gi ni ds. So this is if it is a vector. Suppose it is parameterized. So this much everybody agree, right? Everybody agree this. Agree with this. So suppose this is parameterized by k. Then there's a k here. This is now I of k, and this is I of k. Agreed? The k is in front or back. So k is in. So let's write this one as ki. So I don't have to invoke symmetry or anything like that. It's actually symmetric, but let's leave it like that. Agree? So this k is now just in there for the right. You know, it's just k is equal to 1 to n. K is a free index. This calculation holds. Agree? So having seen that, now you are ready to apply divergence theorem for this quantity without any confusion about where to put the I, where to put the n, k, right? So help me. So what happens to this term? So this becomes integration over the entire domain.
Eta would be eta k or normal vector that may also change, no?
So good point. I should slow down and talk some more. So let's say the k, forget the k, that's fiscal frozen. I control it by, so there's no k here. So, so then if I transform this quantity, first erase it and then we'll come back. You agree with this part? You agree with this part, right? Now I say that, so here it is a vector. Now I want to introduce one more variable. I'll say a bunch of vectors. That's what a matrix is, right? You see a bunch of vectors. So that is this k. So that means that here when I have it is, I had to write it like I put the k in front. So that is what I wrote here. So it is the same formula before, just that the g is now parameterized by one more index. So n stays as ni, correct?
Change k again, then that n could be different one because it's a bunch of vectors g1 to gn, and for that g1 that was n, so that could be better nk, and then there should be gk and nki.
I'm just trying to see whether how you can. You're saying that I should go and also introduce a parameter here. No. So let's. There are not any other. Suppose just I don't put that. Let's go back to that idea again. So you agree with this one, ni, right? So each of these this equation is holds with a certain component, certain direction in I, right? I'm not changing that. So you find that that's
in the right hand
yeah.
side of the box, then v index is I.
Yeah, yeah. Don't make it. Yeah, there's no summation over k. Is I'll tell you when to change k. I know where the difficulties are. These are called muddy points. So maybe I'll let you think about it a little bit. Okay. So all I'm doing is I have a bunch of these equations, right? Each one of them I am summing with same I. Okay. So help me here. Now so this whole thing I am regarding as G of K, right? G of K acting on so this is what I wrote here. If you regard this one as G of so what do I get here? D sigma Ki by dy what? I, that's good, of dy. Okay, so what we have to do now, I can use the whiteboard a bit. Trust me, feel free to slow me down, we'll talk, okay? Because I came here to talk fluid mechanics. So, okay, so we write that equation. I don't want to sort of run over and then, so we write this equation now. First write it in tensor form, we go back and write it in, so now everything is inside this omega t, remember? So it is, if you want, you can bring all of them to left hand side. So it looks like d of rho uk by dt plus the divergence is written again in tensor form. So it is rho ui uk minus, and then we write that guy d of sigma k of I by dy dy, and this is equal to 0. So let's start from here. What is the free index here? K. What is the free index here? K, because there is a summation, invisible summation. Einstein told us that don't keep writing it because he found it irritating, so he got rid of it. So we should also. So there is a summation over I. We never write. And here also there is a summation over I. We never write. So the free index, this quantity behaves like a vector. This quantity behaves like a vector after the summation, and therefore this equation makes sense. So now you go back and say that we want to argue as before. This equality, this identity should hold for any arbitrarily small volume, and therefore the integrand has to be 0. This is saying that there is no delta function like behavior here giving non-zero values and so forth. This is continuous, nice. So since omega t can be arbitrarily small, sort of an engineering argument, but it's also rigorous, can be made rigorous. So the internal, so whatever that is inside, rho uk dt plus d of dy I rho ui uk. I'm going to bring it to this guy to the other side. So it is d sigma ki by dxi. And this equation holds for k is equal to 1 to n. Correct? Via. Did I write via someplace? I have a habit of sometimes raising the index and lowering the index. Yeah. This is not what is called a closed situation. You notice that we wanted to come up with the equations of fluid mechanics, and I managed to introduce one more variable, it looks like. How many unknowns we have encountered so far? Rho, the density, 1. Velocity, n, maybe 3 dimensional, right? So far n plus 1 variable, right? Density and all the components of the velocity. The first equation is just a single equation. Remember d rho by dt, so it's a scalar equation. We have n plus 1 unknown, right? Density and n unknowns. So far, how many equations we managed to derive? Let me write this one also in the vector form for your enjoyment. So it will look like d of rho u by dt plus div of, in y by the way, of rho. So there's a dot here. U tensor product u is equal to div of, in y coordinate, of sigma. More revealing notation, maybe you can put an arrow here, and maybe put a double line here to show that it's a tensor, right? So let's go back to our discussion. So this is called the momentum equation. But are we in a good shape? How many unknowns? Rho is a scalar, right? U is u1 to un, so n unknowns. So between density and velocity we have n plus 1 unknowns, right? How many equations we have so far? Well, there was an equation for density, right? D rho by dt is equal to div of rho u. So that is one equation. And how many here? This is n equation, because you can see this is n equation. It's not clear from how many equations here, right? So you have n equation here, right? So how many equations? So are we in good shape? You are? What is sigma? Actually, a 5-year-old could have asked that question, right? So say, what is sigma?
Stress.
What is sigma?
Stress tensor.
So how many unknowns we have? No, don't make it, my life complicated. Yeah, that's good. N squared in sigma, right? So you have, so those are also unknown. So now these are not the only unknown. You'll say, this Newtonian hypothesis of bringing Newton's second law into the problem is maybe because the first equation is not enough, because you have a density equation, but that's one equation and n plus 1 unknown. So we wrote down the Newton's equation, and so that is this one. But that introduced this stress, which is a matrix, n by n matrix, and if it is 3, like 9, you say. So you have a bunch of some more unknowns, right? So you have 9 more. And then we'll say sigma is sigma ij, or you write sigma ik, right? N by n equal to n squared unknowns. Actually, it's a symmetric, so you can come up with more hypotheses. But right now we don't know what type of fluid it is, whether the fluid behaves differently in different directions. In fact, I think it's called in rheological fluids, they use certain type of fluids in brakes, so that when you apply magnetic field, it has stress in a certain direction as opposed to the other. And therefore, you may have a directional property of these, so the sigma may not be symmetric. But let's say you can symmetric. But how many equations we have? How many equations we have? The first equation we have, continuity equation. This one is how many equations? N equations, right? We have summed over I, right? So it is n equations here. So far you have n plus 1 equation, but we have all these unknowns, right? We have density, velocity, and also stress. So this problem is an example of what is called a closure problem. You try to bring some other thing to close the story, and things doesn't close because you need something else for now stress, right? And So what happens? So what you can possibly do to close this picture? No control yet. Control could have been maybe on the right hand side if it is a magnetic fluid or things like that. But we want to understand how this Navier-Stokes equation came and why we just only talk about water, incompressible, or maybe low speed flight. But more at the foundation level, we okay, everything we did so far is right. Do you know any other concepts? Newton's three laws then don't appear to be helpful. This is the puzzling thing when you go from high school. Everything makes sense, classical mechanics, and then you go to if you particularly in engineering school, this comes fairly quickly to you. This and then you wonder where did this come from? Because the first law, what is the Newton's first law? You help me recall. There is no force, then you will constant speed. The second one is what more or less we applied, right? The third one, if it's in equilibrium, the force. So that's also sort of we applied to come up with this stress concept. So we have exhausted Newton's. No more Newton. So what can we do? Is there any other concepts you come up with? Laws? Executive orders? So that's where what is called the Cauchy principle. A Cauchy principle allows you to, it's a way to close the problem. The way to close this problem is, well, if rho depends on velocity, right, then it's a function of velocity. Sorry, not rho, this sigma depends on velocity, or maybe it's a gradient of the velocity. And then these unknowns are not there anymore, because then these are the unknowns, right? So that's called it's essentially a closure model. When you study turbulence closure models, you come up with various ways of closing the problem because you don't want to introduce any more variables. Density and velocity, and that is good enough. Stress, we had to deal with stress. So it came in the problem, so now we want to close the problem. So we say that we want to come up with a closure hypothesis, so we'll say sigma is going to be related to velocity. It could be also related to density, but in its simplest situation, its velocity is good enough because you essentially deal with local. So the stress, when you say that it is moving with a group, is it remember the velocity difference? Like you want to move, this in that philosophical analogy we took. The group of people want to go in a certain way, and there are some people want to go in the other way. So there's a difference in velocity. So the velocity difference appear to be the right dependence for to close this problem. So the first thing to say is that okay, this sigma depends on the velocity. So this tensor jungle, everybody is comfortable? Not entirely. It's okay? Otherwise we'll talk more, right? I know it's a brilliant confusion he came up with. I was speechless because he wanted to move. So it looks like, okay, now we get rid of all these problems. The first problem equation has no problem with us. We didn't introduce anything new in the sense that we agreed that I want density as a meaningful variable to work with, velocity as the. I don't want anything else, right? Because then you are introducing. So the reasonable thing to expect that it is Stokes and I want to put also Cauchy because it's now I need to go back and breaking up. So hypothesis. So it's reasonable to expect. Now sigma is tensor, remember, is ij. So let's suppress the I and j now so that I don't have to scare you every time. So it's a function of y. I don't need the bracket. Sigma is a function of y and t, right? Correct? Because some quantity I introduce instantaneously at the point. And so I want to say that this is some function of, so let's say it is some function of, it shouldn't look like any of the f we used before, the gradient u. But that's where is it depend on the gradient at this point, time t? Is this meaningful? Is at this point stress. Stress is caused by strain. You know, it's you also, so if you have studied elasticity, you know, pull the thing, the force is so it's related to that. But this is the stress caused by at this point, because that's what I was assuming, that it is a function of the gradient, right, of the velocity. So it's very reasonable to say this is a tensor because this is du, let's say k by dy I. So it's not the dot product here, no dot product here. The dot product is just looking at the trace of that, right, and just putting it as a tensor. So at that time t, is it reasonable thing to say? If again philosophically thinking, you know that if it's a conflict between individuals, you know, you run into some problem and there was a stress, and I don't know, the strain and the difference in opinion that creates a stress, right? We often say that is something happened now, but if you have a history with the person, right, and then right, so the past history of the strain also creates, you know, depending on you want to how you want to deal with the so this means that this assumption of stress at this point at this time instantaneously depends on the strain seems to be very restricted assumption. In fact, it is at the heart of whether the flow is Newtonian or non-Newtonian, and you know, there is all, even in metals, you know, there are shape memory alloys. If they have seen some demonstration, I could remember there was a professor from Virginia Tech brought metal. These metals, when you heat, they go back to their own, the shape it came from. So if he showed a wiggly metal and he heated by and then it went back to something that looks like VT, Virginia Tech, because it goes back to, you know, this. Fluid also, if whether it's Newtonian or non-Newtonian, depends very much on this dependence. So in its simplest setting, first we assume that it's instantaneously and not the past history, right? We could have actually said that this is a function of gradient y u y of t, y of let's say s, from 0 s to t, right? The past, the history of the strain. So that is more like you know, the hereditary aspect of the stress-strain relationship, and this is meaningful. This usually tend to give you an integral differential equation that's for non-Newtonian fluids, and it's also within the realm of because when you now try to develop control theory, and there are examples that may come at you may be non-Newtonian. Anyway, so assumption 1. One is that sigma yt is only depends on f of gradient u of yt. Okay, so this is what you want to first. So the first pay attention to the time. We will look at other aspects of this in a moment. So first, only look at the time. To say that the strain now is causing the stress now, right? So that is this whole picture is called the new. Is attributed to what we are going to follow is attributed to what is called Newtonian. Non-Newtonian fluids are common, and or maybe average behavior of Newtonian fluid when you take various moments and then when you close, the closure can be non-Newtonian. So the turbulence also you have non-Newtonian. So the first step in this Newtonian approximation is that the time is the same time and not the past history, because often that can be expressed through an integral. Assumption 2, two is that sigma only depends on the deformation. What's called the deformation. So deformation d yt is defined as the symmetric part of the gradient plus gradient u transpose. So this is the matrix, that's the transpose of the matrix. I take the average. So the second assumption, sometimes you combine it, but since there is rich literature on these things, let's separate. So we say that sigma only depends on deformation. The third one is probably a little bit more mathematically stated. So is you can see that we are sort of heading our way, right? We are now saying that sigma is a function of this symmetrized tensor of gradient u. So at least at the philosophical level, we replace this by velocity gradients, right? So that part, so we sort of closed the problem, but we had to refine and say what this function should be, what type of functions you can allow for this this closure. So, but let's write it here before proceeding and telling what is the exact relationship. No matter whether I put this relationship or more refined here, I end up closing it, just that this becomes more harder. If it is a functional differential equation, like in Newtonian fluids, fluid which moves like glue, or there are a lot of Newtonian, non-Newtonian fluids in the practical examples, you are still closing it, but this is not a differential equation, is something that defines at a particular point y and a particular time. Integral differential equations involve integration over space and time. So if you deal with non-Newtonian fluids, naturally you are going to have some kind of integral differential equation. If Dr. Balachandran is sitting here, he will love that statement. They have integral differential equation. Anyway, so proceeding in the Newtonian setting, so this we can actually write div of y is a function of some of the symmetric part d, right? So this closes. Remembering that this is d is gradient. So as far as the closure is concerned, I close it because I don't have any new variables besides u. You understand, right? If I somehow find what should be this f, then I close the problem in the sense that I don't have any other new variable now, right? The variables are velocity and the density, right? There's no pressure yet. Pressure will come. Somehow it will going to come naturally. Agree? Because this is what? This is the symmetric part, gradient of u plus gradient of transpose, the whole thing off. So that's usually called Stokes hypothesis. It's also Cauchy is credited. So it's some function of f. We still don't know what is the function of f we should take, right? And But then there is more. So how can we choose this function, and what kind of functions are acceptable? Because many of you have seen the incompressible Navier-Stokes, but where did it come from? But so far we didn't. So what are the assumptions we made? Well, there was literally nothing controversial about the continuity equation, right? Because it looks like calculus. This much is transport theorem. I just wrote down by transport theorem. There's a rate of change of momentum, and then the notion of stress came. It's a little bit puzzling, but it's okay. So then, if you survive there, then you need to now express sigma as a function of the deformation. But I don't know what is this f. So what can you say about this f? The reference I can give you, the best reference to read, is James Serin's book. So how do you find? How would you characterize f more concretely? So the book to read is James Serin. The book is Mathematical Principles of, I continue here, fluid mechanics. And it's in the 1950s. It's actually a long chapter, and often it may have come as a monograph. He wrote as in this book series called Handbook des Physiques, edited by Clive Proust. And there is a good book series of volume to look at if you have a free surface problem and you don't know what condition to put on the free surface. That's the series to go and look at, because there are articles on free surfaces. So this book, this monograph is essentially instantly became sort of James Serin became so famous because it sort of unified many of these ideas and put things in perspective. And so he also brought many things into one picture. A clone of maybe a 1/5 of what he has is with some hyperbolic conservation law added to it. Has a new avatar that is called. There's a book by Chorin and Marsden. It's called Mathematical Fluid Mechanics. So that is a small portion of what so maculatively sort of designed by James Serin. Anyway, so we still don't know what is f is. So if Professor Rajagopal, who is very well known in quantum mechanics here, then he is very interested in what's called this frame invariance. You want to come up with a physical theory, it should be frame invariant, different what coordinate system you are looking at. The physical law should be same. So that is stated in the following ways. In essence, you are trying to see whether you can invoke some new principle so that you specialize this f, how it should look like. So that hypothesis comes like this. So let's say we just deal with 3 dimension. So n is equal to 3. So you say f is a nonlinear function of this deformation should be covariant to Euclidean 3 group of rotations and translations. So you call the E3, I forgot what's the notation for 3-dimensional rotation group. It's I think it's SO3 is okay. Times maybe translation group. So you say that if you study some group theory, there is some group action on the on the Euclidean 3 group, we suppose you have a rotate the coordinate system by this rotation group, or if you translate it, this relationship between stress and strain should be invariant to this rotation group. So the steps are like this one. I write it, it's not hard. So, no, this is better notation is this one. You call it maybe G is equal to E3, right? SO3 is more specialized. Times, let's say, tau of H or something, translation. Okay, so you want, so F to be covariant to G means this relationship TG F this map is equal to F of TG dot, where G actually comes from GAT and TG is the map of let's say R3 into R3 is the representation of the group, is the R3 representation of the group. So this group has elements which are, these are Lie groups, so it's let's say one of the element is G, and this group induces a certain transformation on the in R3, and those transformations are T. So this map should commute with this transformation. Okay, so this also we need this property, as you know, if it's a group acting on TG2 should be TG1 G2 for G1 G2 belongs to the group G. If you don't like the group theoretic expression, all it says is that it is reasonable to expect that this relationship between stress and strain should be invariant to rotation and translation. That's all it is. And it is more fancy way of stating that it should commute. This is a nonlinear map, but it should commute. So if there's a D here, it should act like this one. Then there's a theorem. So if this is covariant to group action of Euclidean 3 group and translation, then F should be given by the following representation. This is proved in Sritharan. There are many variations of it, as you can see that if you don't like certain, if you have fluids which actually don't like this, don't respect this kind of frame invariant properties, then you're going to have other relationships. But there's a theorem if F is covariant to G in the sense I described, then F of D should be given by minus P of I plus lambda of D plus gamma of D squared. So at least this much, so I haven't made any assumptions here. All I said is, okay, it should be a function of the deformation, and this function should be frame invariant, right, expressed in this algebraic way. So it turns out that, we can give you finish a little bit earlier, it turns out that for most fluids, gamma is approximately 0. That leaves F of D is equal to minus Pi plus lambda of D. So this is called the Newtonian. So now in his simplest assumption, right, the way we got to it is we say first of all it depends on the deformation, the gradient symmetrized part of the deformation instantaneously, right? No past history. That still leaves some nonlinear relationship, right, between deformation and stress. So then you go and say that it should, the loss of fluid mechanics, or maybe the fluid itself, it should have this coordinate invariance, frame invariance. That forces this theorem. This is proved in Sritharan book if you are interested in. It says that the only way it can be is something like that. This is a d squared, this is a matrix squared. So if I keep this, you will get a nonlinear right hand side of the in fluid mechanics. Believe it or not, Landau-Lifschitz-Gilbert, when she proved in her effort to prove the Millennium Prize problem, or a good part of her life, also looked at these models, for example, retaining the nonlinear, and showed that if you keep the nonlinearity, yeah, you can prove, and there's some conditions. If this corresponds to a maximal monotone operator and so forth. If you look at the Landau-Lifschitz-Gilbert's famous book, Mathematical Theory of Viscous Incompressible Flow, at the last chapter she says new models for fluid mechanics. And then there she gives a whole family of non-linear relationship between stress and strain, in particular sort of covering this type of models, and show that for those you have global unique solvability. And her argument was that maybe you guys are looking at the wrong problem, why are you? And so for a long time everybody believed it, but then the incompressible case, the case in particular case where this is 0, and also when the density is constant, then, that very special case is remained open. So the Clay committee identified that as a problem of interest. But this is retaining this one or more complex models where the past history is maintained is also important. So you can see that very easily by retaining this, you get a nonlinear stress. The right hand side instead of Laplacian in the conventional Navier-Stokes equation. By retaining the past history, you may get some integral differential equations. So those two are called they attribute to usually non-Newtonian flow. So this much is in books we very quickly arrive at. Now if this is noting that this is gradient plus gradient transpose, if you take divergence, you get that Laplacian. So it all follows very well. So let's go back and reflect how we started. The continuity equation is not a problem. It's just calculus. It looks like calculus, right? Transport theorem. Here also we have the transport theorem produce this part, and then we have to say the force on that volume by the surrounding fluid. When you think of an imaginary omega t, has to be characterized. So we introduced the notion of stress, and that led to all these more scary stuff. A little bit not so. If you are a math student trained mathematically, then it's probably you will be left with a lot of questions here. What is the concept of stress? Maybe when you go back and look at, if you spend more time studying the statistical mechanics derivation, that part is there. Also, essentially, you had to come up with the invented notion called stress. The equation doesn't close. Okay, so the whole thing we did because we are introducing more and more variables. That's not good. So we come back and say sigma should be a function of the symmetric part of the velocity gradient, but that still leaves a nonlinear dependence. So we invoked this frame invariance and got this theorem and arrived at the simplest case is called the Newtonian. If you retain here is non-Newtonian but no past history but nonlinear. If you allow past history, then either you have an integral equation or another differential equation. All these are in the domain of control and stochastic analysis of fluids. What has been the concentration of work has been the very special case of incompressible viscous flow. So there's a lot of work to do, and it's probably, I hope, enough introduction to get you started in the workshop. Okay, and then you are going to give me another 3 hours for introduction, or just did you move any of my Sunday lecture, or what did you do? Or just that's it. We'll talk about it.
So it's not in time to revise, but if participants want to.
Yeah, so we will see how. So the yeah, Utpal originally wanted me to speak Saturday and Sunday too, like this one, and some introductory. But so I have, we have now at least 6 lectures or something, and then so that I can give some reasonable understanding about control theory of fluid mechanics, and maybe at least take 1 lecture and speak about the Boltzmann derivation. It's interesting, and because I should tell you new paths to go rather than just explaining what's the past history, right? Just reading the hard papers. What are the new directions? And new directions may be in non-Newtonian fluids and rarefied fluids and magnetic fluids and relativistic fluids and all that, which are very exciting. Thank you for your attention. The last part hard. This is easy, then that part is a sophisticated part, right? Which theorem? Maybe good for you to go back and read. It's sort of, you think group theory if you have studied and it's useless. Here is a place where depending on whether you want to specialize in group theory or not. If you're an applied mathematician and then you want to understand fluid of various types, maybe it's not frame invariant to the full group, but subgroups. It makes it very interesting, right? There are fluid where if you apply magnetic or maybe nanofluids and different kind of fluids, then we'll beg for a closer study of examination of this theorem and how you head to this one, right? And that's why this is at the heart of it, because the future is may also in part maybe taking another good look. Okay.
Can leave it as an exercise because you assume this is a power series expansion.
Yeah.
And look at all those matrices which are invariant to this.
Yeah.
Only 3 matrices exist and the rest.
Has to be. We had to argue that it's 0. Right. Yeah, that's
I mean, others are not invariant.
Only matrices which are
invariant are just.
So you can leave it as assume that it's a power series in D matrix, and then apply this transformation to argue prove that probably the proof, but they can try to do right. It's a good algebraic
computation.
Yeah, nice thing to do, right? So fluid mechanics is not just only PDEs and derivatives. It's, people wrote many different things to, but that's why you shouldn't look at some research papers and say what is the research point. You want to maybe go back and read Sritharan and what it is, how did this come about, and challenge maybe something is wrong. No one goes. Very few people go and check these things because it's already scary enough. So you say, okay, I'll start with this. But maybe there's more things to discover here. Particularly if you know some of if you know some group theory and things like that, you have some edge because most fluid mechanics cannot handle that type of thing. So you will have some new things to go and maybe take a look. And there's opportunities there. Yeah.
We will thank Dr. Shaiju because he is leaving today and present him a memento.
Oh, okay.
Nice.
Yeah. Good. Very nice.